Okay, so this week we're going to talk about variance reduction methods. Okay. So for this, we're going to look at two types of methods first today. The first one is antithetic variables. And the second type is control variables, okay? Right, okay. So let's talk about the first one. Okay, what are antithetic variables? So, so antithetic variables are like this. Suppose U is uniform 0, 1. Then its antithetic form is 1 minus U, okay? Right? And we know that 1 minus U is also uniform, right? So your antithetic variable has the same, so you have U, you have 1 subtract U, they both have the same distribution, right? So even though their form is different, their distribution is the same, okay? So the best way to see how the antithetic variable can help you reduce the variance of your Monte Carlo estimator is through an example, all right? So let's look at an example here. A simple example, suppose we want to find out this integral, okay? X dx, right? Okay, so of course we know that if you do the usual integral, this will be e minus 1, right? Okay, so this is very simple. If you use the Monte Carlo method, the usual way is to just do the following, right? Because this is actually equal to expectation of e of minus x, where x is uniform 0, 1, right? So for here, you would basically just take, this is what you have learned, right? Okay, so basically your Monte Carlo estimator would be just like this, okay? Okay, clear? Now, let's see, okay. So if you use antithetic variables, then you look at this part here. Now this part here, this x is uniform 0, 1, right? So if you replace it with 1 minus x, basically it's the distribution of this random variable is, so if you replace e of minus 1 minus x, it has the same distribution, right? As e of minus x, okay? So basically you can make a replacement, right? So then instead of one Monte Carlo estimator, you could actually make another one, which is as follows. Let's say I call this Monte Carlo estimator 1. This is Monte Carlo estimator 2, right? So I could also estimate it as following. Okay. Okay. And since both of these expectations are equal to theta, right? You can check very easily that expectation of the first Monte Carlo estimator is theta, and also for the second estimator is also theta, right? Now, if we average these two estimators, right? If we average to these two estimators, their expectation is the same. It's still equal to theta. So this is unbiased, right? If you check this, this is basically just theta plus theta over 2, so it's still theta, right? So this is unbiased for theta, okay? And how about the variance, right? Okay, so we're going to look at the variance now. So now we're going to look at the variance of the Monte Carlo estimators, okay? So this is 1/4, right? Variance of this plus variance of that, and plus 2 times covariance of the first estimator and then the second one, okay? So this is the general form, right? The thing is, because your antithetic variables are supposed to be correlated, right? They work because they are correlated. So let's see here. Now, this is the variance for if your variables are correlated, right? Suppose if your covariance of this is 0, that means if you are using independent variables, then you will only have the first part here, right? Okay. So the trick for variance reduction is to choose, so use antithetic variables such that this covariance here, such that your covariance is negative, right? If your covariance is negative, then this will be less than the variance when you use independent variables, okay? Right, so the trick is to make this part, the more negative is the covariance, the more reduction in the variance you get. Okay, so then we can actually try the following. So the variance of now your theta of MC1 is actually consisting of these things, right? Okay, so basically it is so basically your variance is the variance of this thing, so it will basically be 1/n variance of this, right? Okay, so we'll just basically consider instead of the whole thing, we'll just consider the variance of one of the terms, right? Because at the end you just divide it by a constant, right? So this makes the analysis more straightforward. Okay. So basically this Monte Carlo term here is basically just sum of e of minus xi plus e of minus 1 minus xi over 2, right? And divide by n, right? Okay. So basically, we just need to focus on the term here, right? So we want to find out the variance of this term. Okay. So basically, we want to find out the variance of this term, right? Now, so the variance of this term is equal to 1/4. Variance of e of this plus variance of that plus twice of the covariance of these two terms, okay? So then we need to evaluate this covariance, right? So let me find some space here. So so your covariance is the following. So the covariance of this thing, I'll just drop the subscript, okay? It's the expectation of E of this times this. Subtract the expectation of the product, okay? This comes from your elementary problem steps, okay? Right, covariance of xy, by definition, is the expectation of x minus mu x, y minus mu y, okay? So if you do the algebraic expansion, you will get expectation of x, y minus expectation of x times expectation of y, okay? Which is basically this is your mu x and this is mu y, okay? Right? So you have this thing here. Now the first term will be, we get E of minus 1. Okay. And the second term you have, so basically this is your integral 0, 1 E of this. Okay, so basically this is 1 minus E of minus 1, okay? So 1 minus E of minus 1, right? Okay, and this one is, you don't have to evaluate it, right? Because both of them have the same distribution, so they will have the same expectation, okay? So this is square, right? Okay, and to find the variance, basically you just need to do the expectation of E of minus x squared. So that's E of E minus 2x, okay? So that will be this one, which will give you minus 1 over 2, which will give you 1 over 2, 1 minus E of minus 2, okay? All right. So therefore, your variance here will be, you need to do some algebra over there. So let's try to work out the algebra. Right, so you have variance of E of minus x is 1 over 2, 1 minus this, okay? Plus, sorry, subtract the mean, right? The mean is this part here, that's the mean. Sorry, the mean is okay. The expectation of this, so it's this one, right? Square, okay? Okay. So then finally, this whole thing here, so you can work out the algebra, right? So this will be 1/4. So basically, these two variances are the same. So basically, you get half of variance of this, then plus twice of the covariance, right? So that is this part, okay? Plus twice of this. Which you can see from here, this will be negative, right? Because E of -1 is about 0.6 something, okay? 1 minus this is about, let me see, this is 1.2 something, so this 1 point, so this whole thing will be negative. We can do some calculation later, okay? So this one is, so you plug in the value, so that is over here, this one, right? Okay, so plug in this one, it becomes 1/4 this plus this thing, okay? All right, okay. So then we can do some calculations here. Right, so anybody wants to do this calculation? And try to use R to do the calculation. Okay, just a second. So I'm going to calculate this. Okay, let me see. There might be, so over here there's twice of the covariance. Okay, so forgot this part here. So this has to be let me just write that down. Okay. So that will be, so it's divide by 4 here, right? So plus 1/2. Okay. Okay, so this part here is actually about minus 0.12, okay, roughly. Okay, so right, so need to get this part sorted out.
Doctor.
Sorry?
Asnem cannot join the Zoom meeting.
Okay, okay. All right, just admitted. Okay, just tell me if some of you didn't get inside, right? Okay, thank you. Okay, okay, that's settled, right? Right. Okay, just I think there is maybe some small errors somewhere. Let me check. Maybe this always happens when you do a lot of these small steps, right? So let me just trace back. Um, so this is okay, right? Let me check this again. This should be 2. Should be correct. Okay, this will be 1/2. Okay, so this is correct, right? And then the variance of this will be this thing minus the square, which is basically this minus this expectation is here. So 1 minus this square, right? So this is our thing here. So if you divide by 2, so that will be 1/4. Okay, check in. Okay. So this thing here, you check it using the computer, it is about 0.0327. Okay. So you divide it by 2, this part will be 0.0164. All right. So then, okay. So this part here, if you use variables that are independent, right? So this part is the independence effect, right? Okay. This part here is the correlation effect. Okay. So you see that if the two variables are if they are just independent, right? So they will give you a variance of 0.0164. But when you use antithetic variables, they are correlated, okay? So they are correlated, they have a reduction, right, minus. So from 0.0164, the variance has dropped by 0. Let me see. This should be 0.012 or something. Let me check again. It should be okay. This should be 0. 0. Okay, that was actually not correct. The actual value is minus 0.0158. Okay. So you can see that there has been a very large reduction, right? 0.0164, you shave off 0.0158. That's actually a lot, right? Okay. In fact, after you shave this off, this becomes about 0.0006. Okay. So you can see that in this case, the use of the antithetic variable has drastically reduced your variance. Okay. So in fact, instead of using just either one of these to estimate, if you combine the antithetic variables together to do the estimation, it will lead to an estimator with more desirable properties. Okay, in the sense that the variance is actually smaller. Okay. Okay, so so once we know this, maybe we can try to do some simulations, right? Okay, let me show you a simulation. Okay, so so we go back to the example just now, right? So we're going to simulate, let's say, 10,000 variables. Okay. As usual, we simulate from the uniform. Okay. And then we compute. In this case, our g of x is exp minus x, right? So we then sum gx over n. Okay, you can try to run this. All right. So 0.63 something. So the answer is 1 minus exp minus 1, which is about the same, right? Okay. Now we're interested in the variance reduction here. So let's calculate the variance of g of x. So the variance is 0.032 something, okay? So if we had used the antithetic variable, so the antithetic variable will be just exp of minus x, so that's gx, right? And then you plus exp minus, you replace x with 1 minus x, and then you average this 2, okay? Right? And then, of course, you could try to find out its mean and also the variance, okay? The variance of fx. Sorry, This is just fx. Okay. So the mean is actually about the same, right? It's very close to the answer. The variance, all right? Look at the variance, right? 0.0005, okay, relative to 0.03. So if you look at the variance ratio, right, you compare the two ratios. Variance of fx over variance of gx. Right, it's about the variance of fx relative to the variance of gx is only about 1.6%, right? Okay, you multiply by 100, that will get about 1.6%. Okay, so you have managed to achieve using antithetic variables. You have managed to achieve a reduction of close to 98%. Right? So the variance has dropped by 98% from the variance that if you just use independent variables compared to that, your variance just dropped 98%. Okay. The use of independent would be like, for example, you generate another set of uniform values, right? And then you just average out the independent values. Okay. This is not using, this part here, you are not using antithetic variables because your x and y are independent. Antithetic variables, they are correlated because the reduction depends on the negative correlation, all right? So if you take this part, you run this, in fact, you can actually just do mean of hx, okay? It's the same as sum and divide by n. Oh, I haven't simulated y. Okay, never mind. Okay, so the mean is about the same, but if you look at the variance, right? This variance is 0.016, right? So it's still slightly smaller than if you just use a single one, but relative to 0.005 is still much larger. Okay, so in this case, the antithetic variables successfully reduces the variance by a large margin. Okay. Okay, so I'll pause here for a while and ask you for your understanding. So do you have any questions that you wish to ask about this part here? Any comments from students? No comments? Are you sure you understand antithetic variables so clearly? It may be good if you, as you listen to the broadcast, you also have some paper for you to do some sketching and all that, right? just to follow. Okay, just to consolidate, right? Okay, so we're gonna have some kind of exercise to see how well you do the antithetic variables. Okay, so let's go back to the whiteboard. Okay. Going to clear the board. All right, so suppose you have an integral like this. So you can use antithetic variable also in multiple integrals setting. Okay, so if we're gonna find Monte Carlo estimates, right? So this one, as usual, this will be just expectation of e of x plus y squared xy, right? Where your x is uniform 0, 1, and your y is also uniform 0, 1, right? Independent uniform 0, 1, right? Because it's basically multiplying by 1, right? Okay, and this is over 0, 1, 0, 1, so it's actually a 1 times 1, okay? So basically you just need to simulate like this, the usual case. If you want to do variance reduction, right? Okay, so how should you do the variance reduction using antithetic variables? So variance reduction using antithetic variables, okay? So antithetic variables, remember, you just need to use 1 subtract the uniform, right? So of course, the first one, right? So antithetic variables will have 2 forms, right? The first one is the regular form. So that will be so sorry, this is not the Monte Carlo expectation. Okay, this is this, right? So sorry. So this one will be the summation of e of xi plus yi, right? Square. Okay. The second Monte Carlo estimator, if you use antithetic variables, you will have to replace your x with 1 minus x, right? Okay, the uniform use the 1 minus plus 1 minus yi, okay? Square. So basically, this part here is 2 minus xi plus yi, okay? Right? So your antithetic method would yield an estimator like this. So this part here is e of this plus this divided by 2 and divided by n, right? Okay. So basically, once you simulate a pair, right, you have xi plus yi. You just need to subtract it from 2, right? And then construct a function like this. Okay. So this should give you a smaller variance. So the variance of this should be smaller than the variance of 1 or variance of 2, okay? Right. So let's look at an implementation, okay? Using R. Go to R, yeah. Okay, let me see. Go to my desktop. Okay, back, right? Okay, so I'm just going to modify this part a little bit here. Okay, so that's my x and y. So basically, then I have my my function. Let's say f of x is exp minus x plus y squared, right? And my gx is xp minus 2 minus x plus y squared. Okay. So let's run this. Okay. So you can find the mean of fx, mean of gx, right? This would be the separate estimators. And then of course you can find the average, right? Plus gx divided by 2. That will be the estimator using antithetic variables, right? So these are the separate ones. And the last one is the one that you combine both, right? Let's look at their mean. Okay, they are about the same, right? And let's look at the variance. The individual variances, this should be about the same, but the last one should be much smaller. Okay. Oops. Actually should be copy this, paste. All right, okay. So as you can see, the variance of the Monte Carlo estimator obtained using antithetic variable is much smaller, right? If you look at the amount of decrease, so that will be this one, this variance divided by either one of the variances. Right, so it's only about 2.5% of the variance of the usual form, right? I mean, the first time you learn Monte Carlo estimation, so that's the form that you use. But if you use antithetic variables, it led to actually a reduction in variance of almost 98%. Okay, so of course this type of estimator would be much more preferred than the original form, right? Okay, so any queries about this section? Antithetic variables? Any questions? You need to ask some questions. Let me go back. Sorry, but why do we need to divide for the last one? That is to compare, right? This part here, right? I'm comparing. So this part here, you're asking this one, right? So I'm comparing the variance of the estimator derived using antithetic variables against the variance of the estimator that you usually use, right? You don't need to involve antithetic variables. Okay, this is comparing the two variances. Okay, so as you can see, the numerator part here, this is much smaller than the other one, right? So it's just about 2.5% of the variance of fx. Okay, so fx is just the usual form, right? Which means you have achieved by subtraction, so you achieve about close to 98% reduction relative to variance of fx. So because when you want to achieve compare, right, so you have to have some benchmark. So the benchmark that we use is the standard form of the Monte Carlo estimator. Okay, so we benchmark against that. So there was another question. Doctor, why is there a negative in EXP in the R? Oh, okay. So this part, right? So actually, doesn't matter. The question that I asked was without, right? Okay. Thanks for catching that. Doesn't matter, okay? So we can just rerun this. When you have negative, it just means that it's a different question, right? The idea is the same. So you can rerun this. You can see, right? Okay. So these are the variances, right? So of course, if you divide this, the last one, by the first one, the reduction is about 32. So it's only 33% of the variance of fx. So there's a reduction of 68%. Okay. So for this, in this case, the percentage of reduction is less, right? But of course, if you look at the variance, right, you see this is about 3 times, right? Okay, the variance of the individual Monte Carlo estimators is about 3 times of the estimator using antithetic variables. Okay, so this is a good way to generate, improve the generation of your random variables. Okay, your Monte Carlo, sorry, to improve your Monte Carlo estimates. Okay. Any other questions regarding antithetic variables? So okay, so maybe I can ask you a question, right? You can show me how you use antithetic variables to solve this problem, okay? I just want to make sure antithetic variables is actually quite simple. If you can understand it during this lesson, I think you're basically done with this method, right? Okay, let me go back to okay. You share whiteboard. Here. Right, so I'm going to give you something like this. So your theta is this. Okay, so use antithetic variables to construct a Monte Carlo estimator for theta. Okay, so you spend 5 minutes roughly to get the idea. Okay. So as you can see over here, this is again using uniform, right? So basically your X is uniform, right? Okay. Basically, so this is basically expectation of E of X squared, where your X is uniform, right? So if you're going to use antistatic variable, so what is the first one and what is the second one, right? And then you combine them, right? You combine them and you divide by 2 to average out, okay? All right, so what is this form, yeah? So just quickly work out this form. Okay, so anybody here? Okay. Doctor is only uniform, has antistatic variables or other distribution. Okay. This method applies the antistatic form on the uniform because the idea is I have to have like X and some form like C minus X, both have the same distribution. Okay, that means their distribution must be the same, right? For some kind of C here. The one that is known for sure is the uniform. Okay. Other variables are there are no such properties. For example, normal, you don't have do you have such properties? They don't, right? Let me see, unless minus X. Maybe, let me see. Antistatic variables that are not uniform. That's a good question. The trick is that the distribution must be the same here. They must have the same distribution. I think maybe possible for normal even. If your X is normal, right? Then your minus, let's say your X is normal 0, 1. Your minus X is also normal 0, 1, right? So yeah, possible. But usually we go for the simple one, right? So the simple one will be your uniform, okay? The trick is that the form, right, where there's a negative coming in, right? It has to have the same distribution. So there are not too many distributions that are like that. Okay, good question here. In fact, I think in the textbook, they only show the uniform, right? And didn't talk about the others, but I think it is probably possible to use other forms of antistatic variables, right? They are not uniform. Okay, so over here, so clearly this is, let me see, this one will be summation of E xi squared, right, over n. And this will be summation E of 1 minus xi squared, okay, over n. So basically, this will be summation E of xi squared plus E of 1 minus xi squared divided by 2 and over n, right? Okay. So this guy here, okay, you have already averaged out the antithetic variables, okay? Right, so basically then you can evaluate. So the variances, except for some simple cases, right, you can actually do an analysis of the covariance between the antithetic variables. In this case, it's like this, right? Yeah, in the uniform case, you can evaluate this, okay, no problem. But for more general cases, it will be difficult to do an analysis of the covariance analytically. So usually this is done by simulation, right? Because you can find the covariance very easily in the simulations, okay? After you have generated a value, you basically just compute the covariance, that's all. So it's the concept that's important, right? So let me show you. Go back to the desktop. Okay. So in fact, I can actually look at the covariance of the two the antithetic variables. Okay, I can compute this. In fact, for the previous example, right? You can see the covariance is minus. Okay. You can actually look for the correlation. The correlation is basically just a standardized covariance, okay? So it's minus 0.3 something, right? So the closer it is to -1, the better, okay? I mean, the effect is stronger, right? The variance reduction effect is strong when the correlation is close to -1. If your correlation is actually not close to is close to 0, then the antithetic variables don't help you with variance reduction. There are actually some situations where antithetic variables are not going to help you much. Okay, so in the tutorial you will see one such example, right? So it's not a complete cure for all problems, but it's a good method to try on, right? For example, you could also actually plot the two values, right? To look at the graph. Okay, you can see this, right? Okay, so there's still some curvature here, right? So the covariance actually is if this relationship is more or less like flat, right? Like it drops off like almost perpendicular. That means the correlation is very weak, right? Here you still have a bit of correlation here, which is over this side, right? Okay. All right. So okay with the antithetic variables, everyone. Okay, so now I'm going to cover the next topic, which is also another variance reduction method. This one is called control variables. Okay, let me go back to the whiteboard. Share whiteboard. I'm gonna clear this. Okay, so control variables. All right. Right, so let's see, control variables. Okay, suppose you have the following. Dot theta is equal to expectation of x, right? Okay, this could be some integral, okay? X, gx, dx, right? Where gx is a probability density, right? Okay. This is over all values of x, okay, in the sample space, okay. Now, of course, suppose, right, we have some other variable, y, where the mean is known, where mu y is known, okay. Then, for some c, sorry, for some constant, it's not necessarily positive. For some constant, c, okay. This guy here is also unbiased, right? For theta, okay? Because if you take expectation, right, of this guy, so then clearly this is still expectation of x, right? Because expectation of this part here is actually 0, right? Because you're looking at the expectation of y minus mu y, okay? So that's 0, okay? So this is also unbiased, right? But you can calculate its variance. Okay, so we calculate its variance. Right, so this will be variance of x plus cy, right? Because the other part you expanded is just a constant, right? C times mu y is a constant, so variance of the constant is 0. So over here you have variance of x plus c square variance of y plus 2 times covariance of x and cy, okay? And that will give you variance of x plus c square variance of y plus 2c. This constant you can take out, right? Covariance of x, c, x, y, okay? You can take out because by definition, right? Covariance of, let's say ax and by, right? Is expectation of ax times by minus expectation of ax, expectation of ay, right? Sorry, by, right? So you can factorize ab, okay? So that will be expectation of xy minus expectation of x, expectation of y. So that will be ab covariance of xy, okay? So when you have a constant multiplier for the random variable, you can actually take out the constant just like this, okay? Right, so you have this. So now, once you have this, we want to find out what is C, right? So always we will try to minimize, okay? We want to find the C that minimizes the variance of this function, okay? So let me make some space. So we want to minimize this thing, right? Okay, so you take derivative, right? You differentiate variance x plus this. So maybe I use a shorthand for my variance x so that it is more convenient to write. So like this, plus c squared y plus 2c xy, right? D of this dc, okay? So take the derivative with respect to c, so you get 2c plus 2, right? This is this part here, so you set to 0, right? So therefore, your c is equal to minus the covariance over the variance of y. Okay. You can check that this is the minimum. If you take the second order derivative, it's you d of this, right? D of that over dc2 is equal to 2 of this, right? It's positive, right? So this is a minimum, okay? So we found the minimum, okay? So then you plug in, right? So you can plug in back to this equation here. So finally your variance of x plus, so I put a star here, right? C star y minus mu y is equal to variance of x plus, okay, let me use the new notation. Variance x squared plus this one squared of 4 plus, so it's minus 2 this. Okay, so you can cancel this 2 with this, so you get a 2 here, right? So this becomes variance of x minus actually that's it's actually a square here, right? Because the covariance, okay? So that will be xy over this. Okay? Okay, so you have this thing here, right? So can you see that, of course, definitely this is less than or equals to the variance of x, right? Right, because you are subtracting a positive term, right? Because this is the square of the correlation, okay? So in this case, it's very interesting, right? Because as long as the x and y, as long as your control variable y here is correlated to your x, doesn't matter it's a positive or negative correlation, it will achieve a reduction, right? The stronger the correlation, the better the reduction, right? Because over here, the strongest one is 1, right? Okay. So at best, you can actually achieve a reduction of minus 1 over the variance of y. Okay. All right. So definitely, by this simple trick here, you manage to come up with a method to reduce variance. Okay. So how much is the reduction? So we can again check this by comparing the two variances as follows. Okay, so we compare the variance of this thing against the variance of x, right? If you had used just the usual Monte Carlo estimator. Okay, so you divide this, you basically get one minus this one, right? And this thing here is very interesting. So basically, this is just 1 minus, this is the correlation, right? The correlation of xy squared. Okay? Remember, the correlation is given by the covariance. Correlation of xy is the covariance of xy over the standard deviation of x times standard deviation of y. Okay? The correct correlation is the normalized covariance. The normalization is by the product of the two standard deviations. Okay. So when you square this, right? So you square, so you get basically the variance. Okay. So this is a very interesting result. Okay. So which is saying that if this is close to 1, right? This will be your variance reduction will be very strong. Okay. Because then this will be close to 0, okay? So this is the trick, right? Okay, how control variables are used. Right, okay, so let me go back to the previous example, right? So let me show an example here to see how the control variables are used, right? Here are my drawings. Okay, suppose you want to find out this, right? E of let's say u, right? Du. Okay, so this is expectation of E of u, right? Okay, if you so suppose here, right? So choose the control variable as u. Okay, basically, this is just now, it's like this, right? X plus c y minus mu y, right? So this is our control variable, okay? So in this case here, this part is our E of u, okay? So this part here is our control variable, so we choose u, right? If we choose u, right, so what will happen? So it will be E of u plus c. This is u minus the mean of the uniform 0, 1 is 1 over 2, right? This is 0, 1, okay, uniform. Right? And then what is C, right? So just now we already found out C, right? So C basically is C star, okay, the maximum is the minus of the covariance of xy over the variance of y, right? So in this case, it's the minus covariance of EU u over the variance of u, okay? Right? So over here, so what do we need to do? So the variance of variance of u is 1 over 12, right? We already know that from basic theory. So we just need to find out the covariance of this term here. Okay? So the covariance of this is actually Ez times u minus this, right? Okay, so this one here is basically just 0, 1 x ex dx minus 0, 1 ex dx. This one is 1 over 2. Okay, So this part here, we use part by part integration that will be the following. Okay, minus, so this will be 1/2, 1 e minus 1. Okay, so this part disappears. Sorry, this one you'll get e minus, this part is e minus 1. Okay, so this becomes 1 minus 1/2 e minus 1, which is okay, it's just like that, right? So you can calculate this one, right? So this is about 0.141, okay, roughly. Okay, so we know the covariance here, right? So basically then it's just, so this part here we have EU. So this part minus, so 12 times 0.141. Okay. So then you have U minus 1/2. Okay. So then when you find the variance, so, right? So the variance of this thing, 1 will be equal to, so actually this okay, so C variance E of U plus 12, 0.141 squared variance of U minus 1/2. Okay. So this one you can find out, right? This is E of E2U minus E of EU squared. Okay. So this one over here is basically just variance of U, which will give you 1/12, right? So we'll cancel this part here. Okay. So basically you can do the evaluation. So I leave this to you on the evaluation. You can fill in the details here. You should get something like 0.0039. Okay. Now, so if you use this, the amount of variance reduction is how much is that? It's basically if you calculate just this part, right? So this part, the evaluation is 0.242. Okay, you can check this. So you divide this 0.0039 to 0.242. You get something close to 0.016. Okay, which means you have achieved about a 90.8.4% reduction in variance. Okay. All right, so that's an example of using the control variable. So now I'll show you an implementation in R. Okay. Right. Okay. So so we're gonna draw uniform random variables. Okay, U are uniform 1. Okay, Gx is exp U. So we want to find Gx, the variance, right? Very simple. Okay, so that's the variance of Gx. Okay, the next thing is we look at the so that agrees with your theory. Your theory is about 0.242, right? So this is very close. Of course, it will be not exactly the same because of sampling variation. Okay. So your control variable will have the form exp. Let me put this fx exp. So it will be your gx plus c star, right, times u minus 1/2. So just now, what was our c star? So the c star was minus, let me check, c star, which is minus the covariance of xy over the variance of y, right? So covariance of the covariance of xy will be 0.141, okay, which we estimated just now, divided by the variance of y. So your y here is actually your uniform, okay, your control variable is your uniform, so the variance is 1/12, okay, multiplied by the uniform random variable, subtract 1/2. Okay, so this is our control variable. Right. Sorry, it's just fx. There's no bracket. Sorry. If you have put a bracket, it thinks f is a function, right? Sometimes this happens. Okay. So then you can compare. You can find out your variance of fx. Okay. 0.04. Yeah. So if you compare the variance of fx against variance of gx, right? Okay. So it's about 0.016. Okay. So you achieve close to 98% variance reduction, right? As predicted by theory. Okay. So it's nice to have the theory to back up, but it's really not necessary because this is just to verify, right? Because in a usual case, your integral that you want to find out, right, may be very complicated. So you will not be able to know in advance how much variance reduction you can get, right? But that doesn't affect you because you can always simulate and then find out from the simulation. Okay. All right. So you can actually look at the correlation between. Okay. Let me see. In this case, your E of U and so you can actually plot, right? Plot. In this case, your E of U is your Gx, and you plot it against U. Right? Let's look at the. Right, you can see this, right? So this looks like a very good correlation, right? Okay, almost a straight line. In fact, if you look at the correlation of GXU, right, it's close to 1. Okay, that's why your variance reduction is very powerful here, because the amount of reduction is 1 minus square of your correlation, right? So your correlation is almost 1. Okay, so in this case, why is it almost 1? Can somebody explain? So we have this observation, right? Let me see. We have this observation that the correlation of e power of u with u is almost 1. Why? Correlation of e power of u and u, right, is close to 1. Why? Anybody wants to try? Why is this almost 1? Even without looking at the graph, right, you could actually know that this is almost 1. Why? Any suggestions? Your U is of course uniform 0, 1, right? So why is the correlation close to 1? Hi, you still following, everyone? Yeah, so it actually should be obvious. I mean, at your level, this should be obvious to you. Exponent of uniform roughly falls in the same region. It's unclear what you're trying to say. What do you mean by the same region? Maybe the area exponent and uniform same? What do you mean? What do you mean by the area being the same? Uniform values run from 0 to 1. Power of u will run from 0 to it will run from 1 to 2.71 something. Other students? Let me check. Ayman here or not?
Yes, I'm here.
Ayman. Why?
Mm, not sure, doctor.
This guy here. What do you know about this guy?
And
What are the things that you know about this guy?
mm,
It has a kind of representation that is very useful. What representation?
Representation. Uniform.
No, this function. If you can write it as a series, right? What is it?
Yes. Oh, 1 plus x plus x squared. Gosh.
This is u, right? So
1
it's
plus,
u
1
square
plus
upon
0.
factorial plus this, right?
Yes.
You must remember this, right? This is the Maclaurin series, right?
Yes.
Maclaurin series for exponential function. Okay, now you look at this Maclaurin series, right? For power of u, right? If you look at the power of u, these guys, right? Do you need to consider them? The u square, u cube, and all that, are they necessary? Do you need to consider them?
No.
Why?
Small number.
Okay, because your u is between 0 and 1, right? So u square, u cube, and all that, they will be too small, right?
Yes.
So this is roughly 1 plus u, isn't it?
Yes.
Okay. Then this correlation is roughly the correlation of 1 plus u with u. So can you see clearly now that this is close to 1? Right? Because this is itself, right? The correlation of a variable with itself is 1, right? It's exactly the same, right? This one is just shifted by a constant, right? So basically, it's basically just this is u, this is 1 plus u, right? So instead of like this, it just goes like this, right? So, but then the correlation is still close to 1 because whatever you get, okay, the linear correlation is very strong. So, but of course, this is not exactly, right? It is approximately. So that's why your correlation is approximately 1. Okay, so that's why you know, a lot of these things that you learned before, right? You should somehow you should keep it in mind and activate it when necessary. It will help you understand a lot of things. Okay, especially your infinite series. Okay, please keep that in mind. Infinite series is very powerful, right? When you need to use it, just call it out, and it can be very useful. Okay. Right. Okay, Ayman.
Okay.
All right. Great. Okay. So we are end of time now. Already 4. Okay. So I'll put the recording up later. Okay, and then you can revisit the lecture later when you are free. Right. Okay, everyone. So I'm going to stop now. Okay, and please remember to record your attendance in Flock. I will put up the tutorial 3 later today. Right. Sorry for the lateness. Actually, we probably will just discuss it next week instead of this week. Okay, since I put it up late. All right. And make sure that everyone has submitted your assignment, okay? And you have until 5 o'clock to upload it, all right? Okay, so if you have not done so, please you still have 1 hour to do that. All right. Okay, so that's all for today. All right, see everyone later.